All right, let's start. The IT will come here to check the monitors in a few minutes. But let's start today's class right now. So before we talk about the new stuff we're going to learn today, is there any questions about the first assignment?
Yeah, actually.
Yes.
So the data set you gave us is definitely not linearly separable, yeah? Or is it?
No, probably no.
Okay, cool. Yeah.
So that's why you need to implement the soft margin linear SVM.
Yeah, because I did the hard margin in the dual form, and then CVX was just like, no.
Infeasible, right?
Yeah.
Yeah, that's right. So that means you are not able to find linearly separable hyperplane for this data set. So you put this into the report, right? Say, CVS should give you like infeasible something like that. Yeah. Yes.
For the soft margin, the regularization factor, should I do L1 or L2?
Did we talk about L1 in the class?
Yeah, the class only mentioned L1. But I can't.
Sorry. Did we talk about L1 norm?
Yeah, L1 norm, yeah. On the regularization factors in the soft margin.
Are you talking about the norm, the norm for the W or for the slack variable?
Yes, the mixed calculation.
Well, the slack variable is just the sum of Kasi, right?
Yeah.
And the Kasi is always non-negative.
But it's L1, right?
It's L1, right?
Yeah,
well, in some sense, it's L1. But why you said L2? You mean Kasi square?
Yes, it's this way.
No. No, we didn't mention that in the. I don't see any.
But can you do that in an assignment?
Why you wanna change the sum of Kasi to sum of Kasi square? What's the reason behind that? I don't quite understand.
But I think it's a better result.
Are you sure? Well, you can implement both and do a comparison, right? I don't think so. It's not a good idea to use the slack variables squares to measure the the training error. That will be more sensitive to those noise data, right? It's a square. You basically enlarge the error. Anyway, you can try. You can implement both and do a comparison. Any other questions? All good? All right. So that means the first assignment is a little bit too easy. All right. Next year I will make it more challenging. Okay, that's good. Let's move to today's content. So actually, in terms of classification, we're going to learn some other classifiers in 2 weeks' time about like boosting random forest. The second assignment will also be, implementing AdaBoost, let's say, or boost, or in general ensemble learning methods. So, but I decided to, to introduce some other stuff in between. So today we are going to learn this so-called feature extraction, and in the textbook you might see another term like dimensionality reduction, or feature generation, or feature transformation. They are all the same thing, okay? It's feature extraction or dimensionality reduction. That's the most, common terms. And there are quite a few different methods for feature extraction. But in today's lecture, we are going to just study 2 typical methods. One is called PCA. The other one is LDA. So PCA stands for Principal Component Analysis. LDA stands for Linear Discriminant Analysis. Okay, one is unsupervised. PCA is unsupervised learning. LDA is supervised learning. Actually, LDA can also be used for, learning a linear classifier. And somehow it has some connection with support vector machine, with linear support vector machine. If you want to read more, you can probably Google LDA, linear discriminant analysis, and list squares support vector machines. Actually, mathematically, they are kind of equivalent. Anyway, so let's see, why we need feature extraction. So in the first lecture, in the first week, we said if you want to develop a pattern recognition system, so the first thing you do, step one is collect some data, and step two is, to extract the features, right? So actually, feature extraction is very important, right? Basically, you want to find a representation for the data. And actually, the feature extraction can be complex. The feature extraction itself involves multiple components, right? So I guess you asked me in the first week, say, give an image. What do you do to represent those RGB pixels, right? For example, image classification. So, I mean, in that case, we need to somehow compute those what we call low-level image features. After you get those image features, you can, on top of that, you can do some, manipulation. And today we are going to talk about what kind of data manipulation you can apply in order to get, improved performance. And the PCA, Principal Component Analysis, is just one of those methods. Okay. So today we mainly focus on, still the linear methods, but just the same as the support vector machine, right? We talked a little bit about extending linear support vector machine into kernel nonlinear support vector machine. We actually were able to extend, many of those linear, feature extraction methods into kernel nonlinear methods. But we will have one lecture dedicated to this issue in the second half of the course. Okay, so today we are going to only briefly mention, what a kernel feature extraction method can be, right? So let's just focus on the linear case, which is the fundamental algorithm. So as I said, PCA is unsupervised and LDA is supervised, which means PCA, Principal Component Analysis, you only need the data. You don't need the label, okay? And LDA, you need the label as well. Same as you, say, training a support vector machine. All right. So dimensionality reduction, right? So the high-level idea is very simple. So in most of the cases, in real-world applications, the data you have can have, a lot of features, a lot of dimensions, right? For example, if you use this so-called SIFT feature for image recognition, the SIFT feature itself has 128 dimensions, right? And if you, say, concatenate them, you can easily get, say, thousands of features or dimensions, right? And in that case, you want to project the original data into a lower dimension, say into, for example, 100 dimensions, right? For various reasons that we're going to see why we want to do that. Okay. So there are two main categories of methods to do this dimensionality reduction. So one is feature selection, which is, I believe, as the name suggests, it's easy to understand, right? So given a high dimension data, you just select some of them and just discard the others, right? Let's say you have 1,000 dimensions. You just select 100 and just discard the other 900. Right? That's simpler, right? Of course, the question is, how do you select the subset, right, in order to get a good performance? All right, so there are so many different methods for feature selection, and that we're not going to cover feature selection in this course. We are more interested in feature extraction. Okay, so in feature extraction, in the linear case, what you do is you just basically learn linear projection matrix, okay? And with that linear projection matrix, you just project the original data into a lower dimension, right? So here I just show you example, okay? So basically, say x1 to xd, that's the original data. And after projection, you project the data into a different space, right? Here, the d prime is less than d. That means the projected space is lower than the original one, okay? So that's dimensionality reduction or feature extraction, right? And the second case is actually a nonlinear one. As I said, this is not the main focus of this of today's lecture. All right. So in the linear case, it becomes obvious. So all we need to calculate is the projection matrix, right? That's the main, the matrix variable we need to estimate, right? And for different methods, it's just different approaches to estimate this projection matrix, okay? So in the case of unsupervised feature extraction, that's the original data, right? And in this case, each row is a data point, right? It has d dimension. And each column corresponding to each dimension or each feature, okay? So in this case, we have capital N data points, right? And each data point has d dimensions. So we just collect all the data into this data matrix, right? And then just apply a projection or mapping function. And so that we, after you multiply this projection matrix, you get the transformed data or the projected data, all right? And in the case of supervised feature extraction, you're going to use the label information as well, not just the original data. That's why we need this y. Here, y is just in this case it's a vector. In the simplest case, it's a vector, which means, well, let's say in the binary class case, we have two classes. Then this vector just collects all the label, and each y can be, say, either -1 or +1, right? In the multi-class case, this y, this y1 to yn, each y can itself be a vector, then this y is also a matrix. All right, that's more complex. All right, so let's just check the parametric model of this linear transformation. Right, as I said, it's actually very simple. Here X is the original data, and you just have a projection matrix A, right? And A transpose X just project the data into another space. Right? So mathematically, that's what you are doing here, right? This A transpose, it's a projection matrix, right? The dimension of the projection matrix is D times A is D of size D times D prime, right? So that's why A transpose is D prime times D, right? That's a projection matrix, and that's the original data, right? After you do this matrix calculation, A transpose times X, you get the reduced transformed data in the lower space, okay? So because D prime is less than D, okay? And that's transformed data points, right? D prime is a transformed data point. So, in this way, a straightforward advantage is now, of course, in the projected space, the data is compressed, right? It will reduce the computation complexity for the next stage, right? For training classifier, and another good thing about this procedure is you might be able to remove some of the noise embedded in the original data. Okay, that's actually one of the main purpose for principal component analysis. So it's just a very simple mapping, right? It's a matrix times a vector, right? In the for each data point, right? And there are quite a few different feature extraction or data or dimensionality reduction methods, right? The most typical one is principal component analysis, but there are also, for example, independent component analysis called ICA, and a single value decomposition. There's a very close relationship between PCA and singular value decomposition, right? Singular value decomposition itself is, one of the popular methods in linear algebra. And there's also so-called multi-dimensional scaling, MDS, and canonical correlation analysis as well. For the supervised one, the LDA might be the most popular one. We're going to talk about PCA and LDA. For other methods, like independent component analysis, it also has a lot of applications. If you are interested, you should just Google and read some of the papers. It's developed a long time ago, right? 30, 40 years ago. So with this dimensionality reduction, the first application is, we can enable this, do this data visualization So if the original data is in a high dimension, right? It's let's say 10 dimension or 20 dimensions. It's not possible to plot them, right? So what we can do is we can, project the original data into either, say, 1D or 2D or 3D, right? Then we can use some tools to plot the data and see the distribution of the data points. But if it's higher than 3D, it's 45D, there's no way we can plot them. So one immediate application is data visualization. In most of the cases, we can project it into 2D or 3D. And the other one, as I said, data compression to, reduce the amount of the data for efficient computation and storage, right? And the third purpose is noise removal. So with PCA, in particular with PCA, we can remove some of the noises embedded in the data. And usually we can use this PCA as a pre-processing step. And then, after the PCA dimensionality reduction, we can just discard the original data. And for the remaining steps, you just work on the projected PCA projected data. Okay, so what is PCA, right? How do we calculate the projection matrix? That's all. That's PCA all about, right? So the goal is to reduce the dimensionality of the data while preserving the variation present in the data set as much as possible. Okay, that's the whole idea. And here we just show you a 2D example. Say, we have a bunch of data points in 2D, right? Each data has x1, x2, let's say 2 dimensions, right? And here we just show if you project it into 1D, then that's the direction you project the data, the V1, okay? And in this case, we can find the 2 dimensions, of course, right? Because the original data is 2 dimensions. And the second direction is V2. And as you can see, V1 and V2 are orthogonal. Okay. So the first step we can do is we centered at the sample mean, which means, mathematically, you just calculate the mean of the data and subtract. For each data point, you subtract the sample mean. All right? That means after you do that, that means now you place the original data points, all the data points, into the origin of the coordinate, right? Because now the sum or the average of all the data points will be at the origin of the coordinate. So it's just a straight translation, right? It really does not remove or introduce any, it does not introduce any new information by doing that. And then, for the PCA, you need to find the direction to project the data, right? In this case, we have 2 directions. So the axis 1 has the highest variance, and axis 2 has the next highest variance, and so on. If your data is if your data has more than 2 dimensions, right? We can find the third direction, fourth direction, etc. And another property of this PCA is the principal axes are uncorrelated, right? In this plot, that means, each direction is orthogonal to each other. So in this case, V1 is orthogonal to V2, right? So this angle is like 90 degrees, okay? And mathematically, it means the covariance among each pair of the principal axis is 0, right? If you calculate the covariance, the off-diagonal matrix, all the elements of the off-diagonal elements are 0, okay? Okay, yes?
So that graph in the bottom right-hand corner, that data set was the original data set before principal component analysis has been applied.
That's right.
And the red arrow is the principal axis 1 that has the highest variance.
Yes.
And the blue is
the second one.
With no that is uncorrelated.
Uncorrelated to V1.
Yeah.
That's right.
Yeah. Okay.
So let's say if you want to, in this case, in this particular case, right? Actually, to make the PCA meaningful, you can only project it into V1. If you project it into both V1 and V2, that's the original data, right? Because the original data has 2 dimensions. Okay, let's say if you project the original data into V1, that means you just find let's say for this pixel, for this data point, it will be somewhere here, right? So all the data will lie at this V1, the straight line.
Sure.
All right, that's and on this straight line V1, the variance will be the highest. Right. So okay, so that's a toy example. How I do that? Right. Okay, I already covered that. So the principal components, they are orthogonal vectors that are ordered by the fraction of the total information. Here, information is the variation or the variance, right? Mathematically, in the corresponding directions. And so now the question is how we calculate the so-called principal components, right? We can either use SVD or EVD, eigen decomposition, right? I believe the SVD, singular value decomposition or eigenvalue decomposition, should have been covered by the the linear algebra that you should have taken maybe in the first year. In the first week, I also uploaded some material in terms of linear algebra. So if you don't know what SVD is, what EVD is, just check those material, okay? All right, so let's talk about how we calculate the the principal components, right? So the first thing is you need to do is to calculate this so-called covariance matrix, right? And again, I believe if you have taken some of the linear algebra courses or the basic probability courses, you should know what covariance matrix is and what the physical meaning of a covariance matrix is, right? So, okay, so this here, mu x is the mean of the data set, right? So just remember we have d dimensions. So for each dimension, you just calculate the mean, right? And in the language of probability, that's the expectation of each dimension on this particular data set, right? So it's just the mean. And then what you do is for each data point, you subject to the mean, okay? That's, you centralize the data set, and you calculate this so-called, the covariance matrix, all right? E is the operator of expectation. And, mathematically, that's what you do, all right? So let's introduce a new symbol, x tilde, right? X tilde is just the centralized data. and you collect all the centralized, the means-centered data, and then what, to calculate the covariance matrix is pretty simple. You just calculate the x tilde transpose x divided by the number of the data points. Okay, so that's the expectation of the centralized data times its transpose. Okay. Can anybody tell me? So now this sigma tilde, that's the covariance matrix, right? That's the measured covariance matrix on the particular data set, right? Can anybody tell me what the physical meaning of this matrix is? Right, what kind of information this covariance matrix captures?
It's just the covariance between the feature xi and xj.
Yes, the correlation. Correlation of the each pair of the dimensions, right? That's the off diagonal elements, right? And for the diagonal elements, it's just the variance of that particular dimension, right? So that's the physical meaning of covariance matrix. And of course, it's symmetric, right? This matrix is symmetric. Another good property of this matrix is it's also so-called positive semi-definite. Anybody know what a positive semi-definite matrix is, and what kind of property it might have? Anybody knows? Again, this should be covered in the college mathematics, the linear algebra part, right? So positive semi-definite matrix has the eigenvalues, has non-negative eigenvalues. So that means for any covariance matrix, if you calculate the eigenvalues of this matrix, all of the eigenvalues will be either positive or zero. It cannot be negative. Okay? This is important. Right? And this is highly related to PCA. All right. So, okay, that's covariance matrix. So with the covariance matrix, what you do is you do this eigen decomposition to this covariance matrix, right? Here, PSD stands for positive semi-definite. And if we plot let's check this. It's a 2D toy data, right? If you plot this covariance matrix, then in 2D it's just ellipsoid, right? In 2D it's an ellipsoid. In high dimension it's a hyper ellipsoid. Okay, and so all you need to do is, for PCA, all you need to do is to calculate the covariance matrix and then do the eigen decomposition, right? For eigen decomposition, you don't need to know, how to calculate, how to compute the eigen decomposition, right? They're off-the-shelf APIs you can call in MATLAB or Python. But you do need to know what the high-level idea of eigen decomposition is, right? Why? What it does? What kind of information the eigenvalue and the eigenvector reveal? That's the stuff you need to understand. But you don't need to know, given a covariance matrix, how to calculate the eigenvalue or eigenvector. That's not important, because there are classical methods doing that. And it's very unlikely if you implement, you know, this eigendependency yourself from scratch, your efficiency can be better than those off-the-shelf methods, because it's so important. There are, you know, there are quite a few, you know, very polished API library doing this eigendecomposition. Okay. So let's check what eigendecomposition is. So really, in this case, let's say V is the C is the covariance matrix, right? And in this 2D space, V1, V2 are just the vectors, right? So we have two vectors, V1, V2. And then we have two eigenvalues, lambda 1 and lambda 2. And this covariance matrix can be decomposed in this way. So it's a product of three matrices, right? And the matrix in the middle, that's diagonal. Right? And V1, V2 are just, in this 2D example, there are two vectors corresponding to principal components. Right? So it's very simple to calculate to do this PCA component analysis. Basically, all you need to do is to calculate the covariance matrix, right? So the first three steps is to calculate just to get the covariance matrix, and then you apply the eigendecomposition to this covariance matrix to get the eigenvalue and the corresponding eigenvectors. Okay, so once you have the eigenvalue and eigenvectors, you can sort the eigenvalue from the largest to the smallest, okay? And pick the first few. And discard the others, right? So in this case, let's say we have we pick the D prime eigenvectors corresponding to the largest eigenvalue and put them into the projection matrix, something like this, right? And then you can apply this projection matrix A to reduce the dimensionality of the original data. What if we keep all the eigenvectors, right? So D prime equal D, right? If we do that, then you know the projected dimensionality of the data will be the same as the original data, right? So, you know, that's meaningless, right? And as I mentioned, given a covariance matrix, all the eigenvalues will be non-negative, right? Which means the lambda of the eigenvalues, some of them can be 0. The smallest ones can be 0, right? So in what kind of cases you will have 0 eigenvalues? Okay, anybody tell me? No. The features are completely correlated.
There are two features that are completely correlated.
That's not the general case, right? Just it's related to the. Okay. If some of the features are correlated, yes, right? That will give you 0 eigenvalues. But that's not the general case, right? Okay, so here we need to have this concept of rank, matrix rank, right? So the covariance matrix, if it's so-called rank deficient, then some of the eigenvalues will be 0, right? If it's rank sufficient, then all the eigenvalues are non-zero. In this case, are positive, okay? And let's say, what if the number of the data points, n, is less than d? What will happen? Right? In that case, if the capital N here, the uppercase n is even smaller than the dimension of d, right? In this case, the covariance matrix is guaranteed to be so-called rank deficient, right? And you will have 0 eigenvalues. Okay, mathematically, we can interpret the PCA. We'll connect the PCA with least square error. That's what I mentioned. You know, it can be somehow connected to the least square support vector machines. Okay, not just the LDA, but also the PCA. PCA can be interpreted, reformulated as a so-called one-class least squares support vector machine. So the principal components are linear least squares fits to sample, each orthogonal to the last principal components. Right? And the first principal component is a minimum distance fit to a vector in the original feature space. And the second principal component is the minimum distance fit to a vector in the plane perpendicular to the first PC, right? Orthogonal to the first one. So if you check this figure, that's easy to understand actually. So let's say we have a bunch of data points, right, like this, and if let's say we want to find a straight line, and after you project all the data into this straight line, you want to minimize the least square error. Then you get something like this, right? You get something like this. You project each data point into this straight line, and you measure the error, calculate the least squares error, right? That will be for each data point. This distance will be the error, right? And you calculate the square, the square, and sum them up. If you minimize that error, it's exactly the same as you do PCA. Okay, and in this case, like this direction will be the first principal component. So what you are doing for PCA is the same as least square error minimization. Okay. So here we have another example, right? So given such a set of data points, this will be the direction you find when you minimize the least square errors, and it's the same as the first principal component. And these two explanations are actually equivalent. They are the same, right? One is to find the least square errors, and the second one is to find the maximum variance of the projected data. Right? They are the same. So this here, this will be the projected data, okay? And this will be the least square error, okay? If you minimize the sum of this error, it's the same as maximize the variance of the projected data. Is that clear? All right. If you do some linear algebra calculation, mathematically they are the same. And this idea, it can be extended to nonlinear case. Just a few years ago, around 2005, I believe, 2005, 2006, people invented another method called maximum variance unfolding, MVU. It's somehow just, an extension of the classical PCA method. But that one is nonlinear. It's actually published in Science, the Journal of Science. Okay? So, some nice property of PCA. So, the first property is uncorrelated features, right? That's very easy to derive, right? Because of this, each principal component vectors are orthogonal to each other, and that gives you the projected data for each dimension. They are uncorrelated, which means the covariance, the correlation is 0 if you calculate the correlation. So, which means the xi prime, xj prime, the expectation of this product is 0. So that means, statistically, that means, you avoid information redundancy, right? You just preserve the most possible information, right? And abandon the redundancy. Right? And if you, as I said, if you just keep all the eigenvectors, right? That means d prime equals d. Then the original data can be exactly reconstructed, right? But that's meaningless, right? You are not doing anything. You don't lose information. You don't, introduce any information, right? And when you drop some of the eigenvalues to make d prime less than d, in that case, you drop some of the information, and hopefully that's the either the noise or because of the original data, some of the dimensions are correlated. You don't need them. Which means there's redundancy. Okay. So it turns out, let's say if you keep only, the first a few leading eigenvectors, right? D prime eigenvectors, which corresponds to the largest eigenvalues. We rank all the eigenvalues from the largest to the smallest, in this case, right? Then if you keep the sum of the eigenvalues and eigenvectors, it's the same as, it minimizes the mean square errors between the original data and the projected data. And this can be shown with these equations, right? The squared error, it's actually is just the, in this case, it's just the sum of the abandoned eigenvalues, okay? If you keep d prime, so from d prime plus 1 to d, the sum of this eigenvalues. And for real-world applications, the smallest the smallest eigenvalues usually correspond to the noise in the data, right? If you check the value of the eigenvalues, lambda, in most of the cases you can see, there's a gap between the first few and the last few. There's a big jump, which means, okay, so the first d prime can be the signal, the informative signal in the original data, and the last few correspond to the noise, which you can safely discard, right? And that's how we pick the the dimension, select the dimension. Right? That's one of the criteria we can use. And for each eigenvalue of the covariance matrix, basically, it's a variance of the projected data. Right? You can easily work out this. Okay. So that's why the first principal component corresponding to the largest variance, right? The first one, that's the largest eigenvalue. I might just skip this one. It's easy. Okay, so PCA in computer vision and image processing, I believe it's first applied to face recognition around 1990s, so about 30 years ago. Again, that original paper was published in Science. Now it has maybe tens of thousands of citations. So it's really it has a big impact. So for face recognition, right, of course nowadays for real world face recognition system, we're not using this PCA plus standard machine learning methods. We're using large data plus deep learning. But in old days, before the deep learning methods become popular, it's really, the PCA-based method is really popular. Okay, so let's say we just want to develop a very basic face recognition system, given a bunch of facial images, right? For each individual, you have a few, let's say 10 faces, right? And you want to, the first thing is, given the image data, you want to extract the features. Let's say we want to use PCA to extract the features. What you can do is, you just, each facial image is the original data is a matrix, right? We just flatten the matrix into a vector, right? And then you can calculate the PCA. So once each image is represented by a vector, you can calculate the mean of all the images, okay? And subject the mean for each image, right? And then calculate the covariance matrix and apply eigendecomposition to the covariance matrix. That way, you have the you get the principal components, right? First, a few principal components, and that's the average phase. That's the mean, okay? If you let's say in this case, if you sum all of these phases, and divide it by the number of the phases, then you get something like a blurred version of a phase. That's a mean. That's the average phase. Okay, and we can also plot each principal component, right? Because after you run the eigendecomposition, given the covariance matrix, you can find all the principal components, which are, the eigenvectors. Okay, the first principal component is just the first eigenvector, the leading eigenvector, and as I said, you basically flatten the 2D image into a 1D vector, right? You just you can just convert it back into the matrix from the eigenvector to the 2D matrix. Then you can plot them. So you get something like this, okay? So look, each principal component looks like a ghost face, right? Here we just this is the first one, second one, we just rank them according to the eigenvalues. So now, those are the basis of the projection matrix, right? So really, it just defines a new coordinate for the original data, right? And given any new test data, you just find the linear coefficient for each eigenvectors or principal component, right? And now, in that new coordinate system, you use the weight, the linear coefficient to represent the original data, okay? So let's check this example, right? Let's assume the facial image is, the size is 112 times 92 pixels, okay? The height is 112, the width is 92 pixels. Then the original data is very high dimensional, right? It's 10,000 and 304 dimension, so it's very high dimension. And if we keep the first D prime eigenvectors, then we can project the original data in this way, okay? So into D prime dimension, and this D prime can be very small, right? So what you are doing here, really is given an image, right? And of course you have the average phase is like the offset, right? Plus the linear combination of each eigenvector or principal component, okay? And this is if you keep the in this case, let's say we keep 256. eigenvectors, which means the x prime, the projected data is 256. And then that's the reconstructed face, right? That's the reconstructed face of the original face. If you only keep 256 dimensions, right? You project the original data from, 10,304 to much lower dimension, 256. Then you get something like this. Okay, that's the reconstructed face. All right. And if you somehow sum the eigenvalues from 257 to the original dimension, 10,304. If you sum them up, that's the reconstruction error. Okay. So this PCA is, when you apply the PCA to a new data set, you are projecting the original data into the first few directions found by the PCA analysis. Okay, so here I just give you the when you project the original data into different dimension space, what you have, right? That's reconstructed faces. Okay, so if you keep all the eigenvalues, then the reconstructed face will be exactly the same as the original one, right? And as you can see, if you only keep one, that's you project the data into 1D, right? And you get the reconstructed face like this. And when you increase the dimension, and the reconstructed face becomes closer to the original one, right? That's easy to understand. So PCA is an unsupervised learning method, right? It does not consider the labels of each data point. So it's blind to the class information, right? To the category information, right? It's unsupervised. So the directions of the maximum variance may be useless for classification purpose. Right? You only project the original data into the directions that along that direction, the variance of the projected data becomes the largest. Right? Let's say, just check this plot, check this figure. If we have two categories of data points here, represented by the circles and the crosses. Okay, we have two categories, and if you apply PCA, of course, that will be the direction, right? That direction, if you plot all the data into this direction, the variance will be maximum, and the least square error will be minimum. Okay, but then it's clear that if all the data just lie at this direction, the two categories of data points mixed together, right? It becomes even more difficult to separate. Is that right? So, okay. Can anybody tell me, in this toy example, if we want to find a direction to project the original data, and along that direction, the data should become more easily to more easy to separate. Which direction it should be? Which direction? Definitely not this direction, right?
The opposite direction to that.
Orthogonal to this one, right? Yes. So it should be projected into this one, this direction, right? Such that this class of this set of data points compressed to this part, and this one compressed to the lower part, right? That way, it becomes more, it becomes much easier to separate, right? So PCA is not able to do that. Somehow we must use the label information, and that's what LDA does. That's what linear discriminant analysis does. All right, just a few words before we talk about LDA, a few words about ICA. Right? So the independent component analysis, the main purpose is the transfer dimensions will be as independent as possible. Right? And the transformation matrix can be non-orthogonal. And in most of the cases, we cannot just rely on first order and second order statistics. We need to use high order statistics. Okay, so in PCA, we calculate the mean and covariance. Mean corresponds to the, we call it first order statistics, okay? And the covariance, we call it second order statistics. But they are third order, fourth order statistics, okay? And PCA does not use third order, fourth order statistics, only the first order and second order. But ICA typically use high order statistics. It may use third order statistics, but that's beyond the scope of this lecture. So we're not well, ICA will not be only if you are interested, you can check some of the materials about ICA. So you don't have to understand the details of ICA. Okay, that's the, just to tell you what's the difference between uncorrelated and independent, right? From the meaning of the words, it can be confusing. So mathematically, uncorrelated means the covariance is 0, right? The correlation is 0. And independent, that's, in terms of the probability, which means the given two variables, the joint probability, px1, x2, equals px1 times px2, right? Which means these two variables are not dependent on each other. All right. Again, you don't have to understand ICA. I just, give you the very basic idea. Okay. So what can ICA be applied to? Just give you a very simple application. In speech signal analysis, there is this problem so-called cocktail signal separation, right? Just imagine in a party, there are so many, speakers speak at the same time. And if you record that audio signal, it may have, it's a mixture of multiple speakers, right? And the task is to separate that mixed signal into, individual speaker signal, okay? In the simplest case, let's say we have two persons speaking at the same time, and you want to only given the mixed signal, you want to separate that signal into two, okay? What can you do? Well, the first method you can try is to apply this so-called independent component analysis, right? The objective function of that independent component analysis is to, minimize the dependency of the separated signals, right? By minimizing that, you will be able to, estimate each individual speaker's signal. Okay, that's what ICA can do. As I mentioned in the beginning, I said PCA can be extended to kernel version, just the same as in the case of support vector machine. For now, you don't have to know the detail because we're going to get back to kernel methods later. Okay, basically, well, the high-level idea is actually, again, it's very simple. Just check the what we do about PCA. So, okay, so really, you calculate the covariance matrix of the original data, right? And you apply the eigendecomposition to the covariance matrix. Just remember, last week we talked about the kernel version of support vector machine. You project the original data into another space, right? To make x become phi x, and somehow you don't know the mapping function phi. And in the case of support vector machine, you calculate the inner product of phi xi transpose phi xj, all right, in the due formulation. And here we basically apply the same trick, right? Because when you calculate the covariance matrix, as long as we can calculate the covariance matrix of phi t, then you can just abandon the original data and do the eigendecomposition, right? And this is the so-called kernel trick. Anyway, we will talk in detail about kernel PCA, kernel LDA later, probably in October. So for now, you don't have to. Okay, so that's a high-level idea. For now, you don't have to understand the detail. All right, so that's PCA. Any question about principal component analysis before we proceed to LDA? Yes?
How do you choose the number of dimensions?
Okay, that's a very good question. So how do you choose D prime? One thing you can do is you sort the eigenvalues lambda from the largest to the smallest, and one thing you can do, you plot them. Okay, you plot them, and as I said, the signal part and the noisy part, usually there will be a gap, will be like a jump, and that's one thing you can do. You just pick pick the D prime that the jump happens. Okay, that's one thing you can do, but that's a little bit like a heuristic. Somehow you need to plot the eigenvalues. Another thing, more popular one you can do is once you sort lambda 1 to lambda d, right? And we calculate this so-called signal to signal ratio, let's call it. Okay, so that's the sum I equals 1 to d prime lambda I is 1 to d, and of course d prime less than d. Okay, so maybe some of you can have a look at it later. Okay, So this ratio must be less than 1, right? And in most of the cases, you just, for example, you preset, let's say, let's make it 0.9, right? That means we want to preserve 90% of the signal energy in the original data, okay? And you just pick the D prime satisfy, this ratio no less than 0.9. All right, that's two most popular ideas that you can use to determine, the value of D prime. Okay, that's a very good question. And before you can apply, you must, find a way to calculate the D prime. Any other questions?
Yeah, I had one.
Yes.
Because of this sort of class-agnostic interpretation that we take in things.
That's right. You don't have class labels.
Yeah, is it better for use in like continuous data situations, like regression analysis, than in classification? Or?
No, not necessarily. It's just a data pre-processing, right? And as I said, actually, one of the very important, advantage of the PCA to remove the noise, right? Another thing is to just reduce the amount of the data to make the subsequent processing much faster. So it's not related to classification or regression. You can apply PCA for both problems. Okay. Okay. Now let's move to LDA. So LDA, right? So it's also a dimensionality reduction method, but it uses the label information, and it mainly for it's actually only for classification, right? You cannot apply LDA to regression problems because you don't, in regression, the label is a response, it's continuous, right? Okay, so the high-level idea of LDA is it's just different from PCA. You wanted to find the projection matrix such that for the projected data, the so-called between class distance should be as large as possible, which means after you project the data, let's say in the case of two classes, the two classes of data should be as far away as possible, right? At the same time, so-called the within class or the intra-class distance should be as small as possible, right? So that way, the projected data becomes very easy to separate. Okay, that's the high-level idea, and I believe it's very easy to understand, right? So separating different classes in the projected space, right? We want the after you apply the projections, they should be separated very easily. So this is the PCA, right? It does not use the label information. All right. So in this case, if we project the data into this space, along this line, then these two categories of data points become much easier to separate, right? So not this one, but this direction. Let's assume we have two classes of data points, all right? So we want to find the best direction W that we hope will enable accurate classification. Of course, the projected data will be W transpose X, okay? And we need to define criteria to do that. So the criteria is the first criteria, of course, is that the projected data should be as far away as possible, right? So how we define the distance between two classes? That's the question we need to answer. So the first idea is, how about just calculate the distance of the center of the two classes, right? Here we have the mu1 prime, mu2 prime. That's the center of the projected data of each class, all right? So one thing we can do to make them far away, right? One thing we can do, of course, is to maximize the distance of the center, right? And to remove the scale ambiguity, we just set the L2 norm of the projection metric. Projection in this case, it's a vector, right? We'll project it into 1D. For this case, just make it to be 1. Right? This you can make it to be any constant, okay? Because there's a scale ambiguity. But this only considers the distance between the centers of the two classes, right? It does not consider the variance of the class, because if you look at this two direction, if you calculate the distance, it may be almost the same, but for the first case, the variance of each class is much bigger than the variance of each class in the second case, right? And intuitively, of course, the second case is better than the first case, right? The second case, the two classes, there's no overlap, but this one there's overlap, okay? So that's the idea. We also need to consider the variance, the internal variance for each class, right? Okay. So that's the criteria. So the we want the distance between classes to be as large as possible. At the same time, we also want the variance of each class, right? The variance within each class to be as small as possible. So then in this case, we can use this as a criteria, right? So if we maximize the objective value of J, then you are achieving both purposes, right? Because the distance mu1, mu2 here will be large. At the same time, S1 square, S2 square, that's the variance for each class will be small. Okay? So that's a high-level idea. To calculate the variance of each class, we just use this so-called scatter of the calculate the so-called scatter matrix. Okay, this is a scatters of the projected data. Basically, it's the if the project data is 1D, then it's just the same as the variance. Right? If it's high dimension, then it's a matrix. Right? If it's a matrix, we cannot just simply calculate the square. In this case, it's let's assume we just project it into 1D. Okay, then that's the simplest case. So that's what we have. We just maximize this one. All right. In high dimension, we just calculate the so-called between class scatter matrix and the within class scatter matrix, and the distance can be calculated as W transpose SB W transpose, right? So that's the after you project it into 1D, that's the distance, and the W transpose SW times W, that's the within class variance, right? But here, of course, we assume W is a vector, which means you project the data into 1D, all right? If you write the objective function this way, you are projecting the original data into only 1D, okay? Not high dimension. So, all right. So how do I find the W, the projection matrix W? In order, well, given such a objective function, to maximize J, right? In terms of W, we can just calculate the gradient, right? At the optimum, in this case, either minimum or maximum. At the optimum, the gradient vanishes, right? The gradient should be 0. So we calculate the partial J, partial W, and make it to be 0. And then we get something like this, right? I just skip the, you can work out. This is pretty straightforward, right? And then you get something like SB times B times W equals lambda SW times W. This is a so-called generalized eigen decomposition problem, okay? If you times the inverse of SW to both sides, then you get something like this, okay? Then this becomes a standard eigen decomposition problem, right? We just need to find the eigenvalue and eigenvector of SW inverse of SW times SB, okay? So we can solve the eigenvalue problem, same as in the case of PCA, right? Okay, so that's the steps of LDA. You calculate the mean of, we assume we have two classes, okay? You calculate the mean of the two classes, and also the so-called scatter matrix. And then you calculate the SW and SB, right? And then you apply the eigendecomposition. You find the W. All right. So here we just project the data into 1D, right? Actually, the rank of this matrix, the inverse of SW times SB, the rank of this this matrix is no more than 2, right? The rank can only be 2, right? Okay, so then we can find the eigenvalue, right? Eigenvalue and eigenvector. The W is the eigenvector, right? Corresponding to the largest eigenvalue of inverse SW times SB. And once we project the data into 1D, we can just find a threshold and do the classification. So that means after you apply LDA, you can, it's also a kind of a classifier in the case of you have two classes. Right? How about in the case of multi-class, right? We all the above formulation are based on the assumption that you have two classes. What if we have more than two classes? So it's easy to extend, right? You just redefine SW and SB. Right? You just calculate the scatter matrix for each class, and then use all of the scatter matrices to calculate SW and SB. This is just an extension of the two classes. And in this case, you can find C minus 1 projecting directions, right? In the case of C equals 2, which means C is in the number of classes, you can only project it into 1D. But now you can project it into, higher than 1D, right? So the eigendecomposition is still the same, right? You just apply it to SW transpose times SB. The physical meaning of multi-class LDA now somehow is different, right? Because in the multi-class case, this W transpose SB W will not be a scalar, because W will be a matrix, right? A matrix times SB, of course, is a matrix. Again, W is a matrix. It's not a vector. So this product of the three matrices will be a matrix as well. And of course, W transpose SW and W, this is a matrix as well, not a scalar. Only in the scalar, only if they are scalars, you can just directly calculate the objective value, right? In the case of matrix, you cannot do that. So then the extension is we calculate the determinant of the scatter matrix. So the object function now becomes slightly different, okay? Because W transpose, again, W is a matrix now, right? It's not a vector. In the case of two classes, W is a vector, right? You project the data into one dimension, into one direction. So now instead, because this is a matrix now, so we just use a determinant. If you don't know what a matrix determinant is, maybe check Wikipedia, okay? Check Wikipedia to see how do you calculate the determinant of a matrix. Basically, given a matrix X, you calculate all the, in this case, this will be a positive semi-definite matrix, right? All of the eigenvalue will be non-negative. So the determinant of this matrix is just the product of all the eigenvalues, okay? So the solution of this object function, if you want to maximize it, again, it's a generalized eigendecomposition problem. It's the same as in the case of we have two classes, C equals 2. Okay, it's the same. All right, so the rank SB, sorry, what I said is previously is wrong. The rank of SB is no more than C minus 1, not no more than C, okay? So that's why in the case of we have two classes, C equals 2, the rank of SB can only be 1. That means we can only find one non-zero eigenvalue for this eigendecomposition problem, okay? So that's why when C equals 2, we can only project the data into 1D. Right? So at most, C minus 1 non-zero eigenvalues. Right? And the desired weight vectors corresponding to those non-zero eigenvalues. Okay. instead of using the determinant, calculated determinant of the scatter matrix, we can also calculate the trace. Okay, we can also calculate the trace of the scatter matrix. That's just another criteria. And again, the solution is given by generalized eigenvalue decomposition. Again, if you don't know what a trace of a matrix is, check Wikipedia. Right? In the case of determinant, it's a product of all the eigenvalues. In the case of trace, it's a product of all the, sorry, it's a sum of all the eigenvalues. Okay? If somehow the two classes, you know, the center overlap, then right, it becomes clear that LDA will fail, right? Because you are not able to separate them, right? If the the center of the two classes, they are at the same point, right? And if the classes are non-linearly separable, which means, you know, after you project the data into the another direction, there will be overlap. That means it's non-linearly separable, right? We need we cannot just use the LDA to do the classification. All right. Some problem when you do this LDA decomposition, LDA analysis. So if the number of data points is less than d, then you know we have this so-called singularity problem, because you just simply cannot calculate the inverse of the matrix SW. Okay, this one. As the inverse of SW does not exist, right? You have to somehow regularize SW. Or you can first apply PCA to reduce the dimensionality, right? To reduce D, to make it larger than n, sorry, smaller than n. Then apply LDA. So that's a popular approach. You first apply PCA, then apply LDA. Okay. Of course, there are some other variants. That's out of the scope of this class. To summarize, LDA typically provide more suitable features for classification tasks, and but PCA may be able to outperform LDA in some of the cases, right? For example, when the number of samples per class is small, this is so-called overfitting problem in LDA. And when the training data are non-uniformly sampled, the underlying distribution, which means the sample, the training data available to you are a not good representation of the real problem, the real data. Or when the number of the desired features is more than C-1. As I said, in that case, you have to apply, for example, PCA first, then do LDA. And we can also extend LDA to nonlinear case using the so-called kernel trick. Again, we're going to talk about that later. All right, so that's all for today. You are expected to understand, the ideas of PCA and LDA. You don't have to understand ICA or other dimensionality reduction problem. Okay, so that's all.